All right, we got a theorem here that we're going to use over and over and over again this quarter. So I'm going to take some time to go through the theorem and the proof of it. So the theorem is this. If A is an n by n matrix, then the following statements are equivalent. This means that each of these is, if one of them is true, they're all true, or if one of them is false, they're all false. So for an n by n matrix A is invertible is equivalent to saying that AX equals 0 has only the trivial solution. AX equals 0, this is a homogeneous system of linear equations. A is the coefficient matrix, X has all the variables in it, and then a bunch of zeros over here. Okay, so A is invertible is equivalent to the homogeneous system having only the trivial solution, where A is the coefficient matrix. The reducer echelon form of A is the identity matrix. And A is expressible as a product of elementary matrices. Okay. If you know any one of these equations is true about A, sorry, any one of these statements is true about A, then you know all the others are true as well. Okay. One of the things we're going to be doing is just saying, how can you tell when A is invertible? Or if you know A is invertible, what can you do? What does that help you do? So if you could show the reducer echelon form is IN, then you know A is invertible. You never found the inverse, but you know at least that it's an invertible matrix. Okay, so we're going to prove this now. How do we prove that this is true? Proof. Well, to show that they're all equivalent statements is, there's different ways we can do it, but essentially what we're going to do is we will show that part A implies part B, which implies part C, which implies part D, which in turn implies back to A. So if you know A is true, then you would know B, and if you know B, you know C, and then so on, but loop it back to the start here. Okay. So we do this. How do you show that one statement implies another? Well, you have to assume the first one's true and show that the second one's true. So we're going to start off here with assume that A is true. So assume that matrix A is invertible. Right. Now I want to try to show that the homogeneous system here has only the trivial solution. So let's assume that that x0 is a solution to AX equals 0. So assume I have a solution to the homogeneous system. What I want to show is that it's got to be the trivial solution. I mean, I know that the trivial solution is a solution here. So if I have any other, let's show that it's trivial. So to say that this is a solution to that means that AX0 equals 0. Now A is invertible, so A has an inverse. So I'm going to use that inverse and multiply this thing both sides by A inverse. Well, A inverse times 0 is just 0. Again, that's a 0 matrix. I can regroup here and have A inverse A times x0, but A inverse A is just the identity matrix, and identity matrix times x0 is just x0. So the thing is, if you have a solution to this system, then you can show that the solution has to be all zeros, and so we have only the trivial solution. So what I've shown here is that assuming A, I showed that B had to be true. So if A is true, then B is true. Okay. So now we move on to the next one. Let's assume, so now assume that B is true. That is, assume that AX equals 0. That's not the notation I'm using, but it has only the trivial solution. Again, these little symbols over those are just denoting that these are column matrices, single column. Okay. Well, assume that AX equals 0 has only the trivial solution. So the system that this corresponds to the system is, A11 x1 plus up to A1 n xn equals B1 all the way down to AN1 x1 plus ANN xn equals Bn, right? Well, to solve this, I'd make an augmented matrix, put it in reduced row echelon form, but I know that the reduced row echelon form ends up looking like this. Well, ends up looking, how do I want to say this? This is not any, this is the solution, right? It boils down to the trivial solution, and this is the only thing. So the augmented matrix must, the augmented matrix put into reduced row echelon form looks like this. One's down here, zero's in this last column, and zero's everywhere else here, right? So this is the reduced row echelon form of the augmented matrix. Notice just this part here would be the reduced row echelon form of A. Would be just that part right there. And that is part C of my theorem, right? So that the reduced row echelon form is IN. Okay, so if there's only the trivial solution, then this system must turn into this, which means that the augmented matrix, the reduced row echelon form of the augmented matrix looks like that, which means that the reduced row echelon form of A is just IN. Okay, and so that was the proof that B implies C. Okay, so now I'm going to move on and assume C. So now assume that the reduced row echelon form of matrix A is the identity matrix, and I want to show that I can write A as a product of elementary matrices. Well, the thing that we did with elementary matrices at the end of the last video is we showed that we can use multiplying by elementary matrices to do row operations. Well, there's a sequence of row operations that turns matrix A into an identity, right? There is a sequence of row operations that turns A into IN. So what I want to do instead is think of those row operations as saying, we'll start with A, and what we're going to do is we're going to multiply by an elementary matrix corresponding to the first row operation that you use. And then you're going to multiply by E2, which would be the second row operation in this sequence, all the way up to E, I don't know how many there are, K, that multiplying A by each one of these elementary matrices would be the same as taking A and doing the same sequence of row operations, and you know that that boils down to the identity matrix. Now, I note that each one of these row operations is invertible. So I'm going to multiply, first of all, by EK on the left, and then I'm going to multiply by this one on the left, and then that one on the left. So what I have is I'm going to end up with just A on this side, and I've got IN. The first thing I multiplied was by EK inverse, and then EK minus 1 inverse, and then all the way down to E1 inverse. Right? But notice I can, well, multiplying by I doesn't do anything. So I have A equals E1 inverse all the way up to EK inverse all multiplied together. And so A is a product of elementary matrices. Suppose I should point out that not only are elementary matrices invertible, but their inverses are also elementary matrices. So these are, in fact, elementary matrices, and A is a product of elementary matrices. So that was C implies D. And finally, we say, assume that A is a product of elementary matrices. The pen seems to be able to keep up with me today, which is nice. Well, each of the elementary matrices is an invertible matrix. So A is a product of invertible matrices. And what do we know about a product of invertible matrices? The product of invertible matrices is invertible. So A is invertible. In fact, you can kind of see it up here that if A is this bunch of elementary matrices, then you take all the inverses of these elementary matrices and multiply them by A right here, you're going to get IN. So then it is, in fact, the inverse. Okay. So, assume that it, so this was D implies A. So A implied B, B implied C, C implied D, D implies A. So any one of them implies any of the others, and we have proven that they are equivalent.